Hello there. Tonight, we drift into something invisible, something that fills every corner of the universe. Yet, we've never touched it, never seen it, never held it in our hands. It's not hiding in shadows or lurking in distant places. It's here, right now, in the space between your fingers, in the air around you, woven into the fabric of everything that exists. Scientists call it dark energy, and it's the strangest thing we've ever discovered. This invisible force is quietly, gently, pulling the entire universe apart. If you enjoy these quiet journeys into the mysteries of science, if this kind of wonder brings you calm or sparks your curiosity, take a moment to like this video and subscribe to the channel. It helps other scientific wanderers find their way here too. And tell me in the comments where you're listening from and what time it is there. There's something beautiful about knowing we're all under the same vast sky, exploring the same mysteries together. But for now, let yourself sink deeper into comfort as we explore this cosmic secret. Dark energy makes up most of our universe, about 68% of everything. Not stars, not planets, not the gas between galaxies, or the dust that forms new worlds. Just this strange, visible pressure that permeates all of space. And yet, for most of human history, we had no idea it existed. Think about that for a moment. The dominant force in the cosmos, the thing that controls the fate of literally everything, was completely unknown to us until very recently. We looked up at the stars for thousands of years, built telescopes, sent probes into space, and still missed the most abundant thing in existence. It's not our fault, really. Dark energy doesn't glow. It doesn't cast shadows. It doesn't pull on things the way gravity does. Instead, it does something far stranger. It pushes. Everywhere, all at once, dark energy creates a gentle, constant pressure that's stretching space itself. Imagine the universe as a vast ocean, and dark energy as an invisible current flowing through every drop. You can't see the current, can't feel it on a small scale, but it's there, moving everything, shaping everything. This current doesn't flow in one direction. It flows outward, in all directions at once, pushing every distant galaxy away from every other distant galaxy. Right now, as you rest here, billions of galaxies are rushing away from us, carried by this invisible tide. And they're not just drifting, they're accelerating, moving faster and faster with each passing moment. The universe isn't just expanding like a balloon being slowly inflated. It's expanding faster and faster, like a balloon being inflated by someone who keeps blowing harder. This acceleration, this cosmic speeding up, was one of the most shocking discoveries in the history of science. It won a Nobel Prize. It changed everything we thought we knew about the universe's past and future. And it all came from studying something we can actually see. But to understand this invisible force, we need to start with something visible, something concrete and real. We need to look up at the night sky and really see what's there. Because hidden in the light of distant stars is a message, a clue written in the language of physics, telling us that our universe is far stranger than we ever imagined. So let's begin there, with the simple act of looking up, with the photons of starlight that have traveled unimaginable distances just to reach your eyes. Picture yourself outside on a clear night, away from city lights, looking up at the stars. Each point of light you see is a sun, often much larger than our own, burning billions of miles away. And the light from those stars, the photons hitting your eyes right now, have been traveling through space for years, sometimes centuries, sometimes thousands of years, just to reach you in this moment. That light carries information. It tells us how hot the star is, what it's made of, how fast it's moving. And in the early 1900s, astronomers started paying very close attention to light from the most distant objects they could see, the fuzzy patches in the sky they called nebulae. Some of these nebulae turned out to be entire galaxies, island universes containing hundreds of billions of stars, so far away that their light takes millions of years to reach us. A man named Edwin Hubble, using one of the largest telescopes in the world at the time, made careful measurements of this light. He noticed something odd. The light from distant galaxies was stretched, shifted toward the red end of the spectrum. We call this redshift, and it happens when something is moving away from you. It's like the change in pitch of a siren as an ambulance speeds past, only with light instead of sound. But here's what made Hubble's observation truly remarkable. Every distant galaxy he looked at showed this redshift. Every single one was moving away from us. Not just a few in one direction, but all of them, in every direction he looked. The farther away the galaxy, the faster it seemed to be receding. At first, this might sound like we're at the center of some cosmic explosion, like everything is fleeing from us specifically. But that's not what's happening at all. Imagine dots drawn on the surface of a balloon. Now inflate the balloon. Every dot moves away from every other dot, not because the dots themselves are traveling across the rubber, but because the rubber itself is stretching. The space between the dots is growing. That's what's happening to our universe. Space itself is expanding. Galaxies aren't racing through space away from us. The space between galaxies is growing, carrying them apart like dots on an inflating balloon. This was a revolutionary idea, one that completely changed how we understood the cosmos. The universe, we realized, is not static and unchanging. It's dynamic. It's getting bigger. And if it's getting bigger now, that means it must have been smaller in the past, much smaller. Wind the clock back far enough, and you arrive at a moment when all of space, all of matter, all of energy, everything that exists, was compressed into an incredibly hot, incredibly dense point. The Big Bang, the beginning of everything we know. For decades, this picture seemed complete. The universe began in a hot, dense state and has been expanding ever since, gradually cooling as space stretched out. Gravity, pulling galaxies together, would slowly break this expansion over time. Eventually, scientists thought the expansion might even stop or reverse, pulling everything back together in a big crunch. They had the measurements. They had the mathematics. They thought they understood how the story would unfold. But here's where it gets truly amazing. They were wrong about what would happen next. The balloon analogy is worth staying with for a moment because it captures something essential about how space itself behaves. When we say the universe is expanding, we're not talking about galaxies flying through empty space like rockets. We're talking about space itself, stretching, growing, creating more distance between things. Imagine you draw two dots on a deflated balloon with a marker. They're close together, maybe an inch apart. Now you start blowing up the balloon. As the rubber stretches, those dots move farther apart. But the dots themselves haven't moved across the surface. They're still sitting in the same spot on the rubber. The rubber itself has grown, carrying the dots with it. Draw more dots all over the balloon before you inflate it. As you blow it up, every dot moves away from every other dot. If you were standing on one of those dots, you'd see all the other dots receding from you in every direction. And here's the key part. The dots that started farther away would appear to move faster, simply because there's more stretching rubber between you and them. This is exactly what Hubble observed. Nearby galaxies showed small redshifts moving away slowly. Distant galaxies showed larger redshifts moving away faster. The relationship was clean and clear. The farther away something was, the faster it receded. This relationship, now called Hubble's law, told scientists that space itself was expanding uniformly, stretching everywhere at once. For decades after this discovery, physicists worked to understand the details. They knew the universe was expanding. They knew it had started from a hot, dense beginning. And they knew that gravity, the force pulling all matter together, must be slowing down this expansion. Like a ball thrown upward that gradually slows as Earth's gravity pulls it back down, the universe's expansion should be gradually decelerating. The math supported this. The observations seemed to fit. Galaxies were flying apart, yes, but gravity was doing its job, pulling them back, slowing the cosmic expansion bit by bit. Given enough time, maybe the expansion would stop entirely, or maybe it would continue forever, but at an ever-decreasing rate, gradually approaching zero, but never quite getting there. Scientists built models of the universe based on these ideas. They calculated how much matter existed, how strong gravity's pull should be, how fast the expansion should be slowing down. They designed experiments to measure this deceleration precisely. They wanted to know the universe's fate. Would it expand forever, or eventually collapse back on itself? The answer, they thought, would come from studying the most distant objects they could see, from measuring exactly how the expansion rate had changed over billions of years of cosmic history. They needed cosmic yardsticks, objects so bright and so consistent that they could be seen across vast distances, allowing precise measurements of how fast the universe was expanding at different times in the past. They found those yardsticks in exploding stars, supernovae of a particular type that always shine with the same peak brightness. By comparing how bright these explosions appeared from Earth with how bright they actually were, scientists could calculate their distance with remarkable precision. And by measuring their redshift, they could determine how fast they were moving away. Two independent teams of astronomers began this painstaking work in the 1990s, studying dozens of these distant supernovae, building a detailed picture of cosmic expansion over billions of years. They expected to measure how much gravity had slowed things down. Scientists thought they understood this expansion. They were wrong. In 1998, two teams of astronomers announced results that stunned the scientific community. They had studied distant supernovae, those exploding stars that serve as cosmic measuring sticks across billions of light years of space. They had carefully measured distances and redshifts, plotting how the universe's expansion had changed over time. And what they found made no sense. The universe wasn't slowing down. It was speeding up. Imagine throwing a ball into the air and watching it climb higher and higher, accelerating upward instead of falling back down. That's how strange this discovery felt. Everything we knew about gravity said the expansion should be decelerating, braking, gradually slowing down over time. But the data showed the opposite. Distant galaxies were receding faster than they should be if gravity were the only force at play. At first, the scientists checked and rechecked their measurements. They looked for errors in their calculations, problems with their telescopes, mistakes in their reasoning. Maybe dust between our and those distant supernovae was making them appear dimmer, throwing off the distance measurements. Maybe the supernovae themselves weren't as consistent as everyone thought. Maybe something about how light travels across cosmic distances had been misunderstood. But the more they checked, the more certain they became. Both teams, working independently with different telescopes and different supernovae, found the same result. The universe's expansion was accelerating. Something was pushing galaxies apart, working against gravity, making space stretch faster and faster as time went on. This wasn't a subtle effect or a tiny discrepancy. This was a fundamental rewriting of cosmic history. For about the first half of the universe's life, gravity did slow the expansion, just as expected. Matter was dense enough that its gravitational pull dominated. But as space expanded and matter spread out, becoming less dense, something else began to take over. Some kind of energy, filling all of space, began pushing outward with enough force to overcome gravity's pull. The accelerating expansion meant that this mysterious energy didn't just exist, it was becoming the dominant force in the universe. As space grew, there was more space for this energy to fill, and so its influence grew stronger. Meanwhile, matter spread thinner, its gravitational pull weakening. The balance had tipped. The push now exceeded the pull. Think about what this means. Right now, at this very moment, every galaxy beyond our local neighborhood is accelerating away from us. The speed at which they recede is increasing. A galaxy that's moving away at a certain speed today will be moving faster tomorrow, and even faster the day after that. The universe isn't just getting bigger, it's getting bigger at an ever-increasing rate. This discovery earned the Nobel Prize in Physics in 2011. It was that profound, that revolutionary, that important to our understanding of the cosmos. In one set of observations, scientists had uncovered evidence for a completely unknown component of the universe, something that apparently makes up the majority of all energy in existence. But discovering that something exists and understanding what it is are two very different things. The astronomers had found the effect, seen the acceleration, measured its strength. Now they needed to give it a name, even though they had no idea what it actually was. Something was pushing the universe apart, something we'd never seen before. Scientists needed a name for this mysterious force causing the universe to accelerate. They chose to call it dark energy, though the name is somewhat misleading. It's not dark in the sense of being shadowy or sinister. It's called dark because it's invisible to us. We can't see it, can't detect it directly with any instrument. We only know it exists because of what it does, because of its effect on the expansion of space. The word energy in the name is also a bit tricky. In physics, energy takes many forms: heat, light, motion, the energy stored in chemical bonds or locked inside atoms. But dark energy doesn't seem to be like any of these. It's more like a property of space itself, a kind of pressure or tension woven into the fabric of the universe. There's something beautifully honest about this name. Scientists were essentially saying, we've discovered something enormous, something that makes up most of the universe, and we have no idea what it is. So we're going to call it dark energy, and admit that we're working in the dark here, searching for answers. This kind of humility is rare and valuable. It would have been tempting to give it a more impressive, more knowing name. But the truth is, dark energy remains one of the biggest mysteries in all of science. We know it's there. We can measure its effects with remarkable precision. We can calculate how much of the universe's total energy budget it represents. But we don't know what it actually is, where it comes from, or why it has the properties it does. Think about how strange this situation is. Imagine if you came home one day and found your furniture rearranged, your books reorganized, your entire house subtly different. You'd know someone or something had been there, even if you never saw them. You could study the changes, measure the differences, figure out what was moved and in what order. But you still wouldn't know who did it or why. That's roughly where we are with dark energy. We see its effects everywhere we look in the cosmos. The accelerating galaxies, the stretching space, the changing expansion rate over cosmic time. All of these are fingerprints left by dark energy. But we haven't caught it in the act. We haven't directly observed the thing itself. What makes this even more remarkable is the sheer scale of what we're talking about. Dark energy isn't some minor component hiding in the corners of the universe. It's the dominant form of energy in the cosmos. About 68% of everything that exists is dark energy. Regular matter, the stuff that makes up stars and planets, and you and me, accounts for less than 5%. The rest is dark matter, another mystery entirely, though at least we understand dark matter's gravitational effects better. So, the universe you live in, the cosmos that contains everything you've ever seen or touched or known, is mostly made of something completely mysterious. 2/3 of reality is this invisible force that we've only just discovered and barely understand. This invisible force doesn't just exist in distant galaxies or the vast voids between galaxy clusters. It's here too, all around you, filling every cubic inch of space, including the space between the atoms in your body and the air you breathe. But its effects are only visible across immense distances. Right now, in the space around you, dark energy fills every gap between every atom. It's in the air between your hands and your face. It's in the space between the molecules of oxygen you're breathing. It pervades the room you're in, the building you're in, the entire planet. There's dark energy in the space between Earth and the Moon, between the Sun and the outer planets, between our solar system and the nearest stars, but you can't feel it. Objects nearby don't accelerate away from you. Your coffee cup stays on the table. The moon doesn't spiral outward from Earth. On these small scales, dark energy's effects are completely overwhelmed by other forces. Gravity, electromagnetism, the simple friction of surfaces touching each other. All of these are vastly stronger than dark energy. When we're talking about distances of inches or miles or even light years, think of it like a river's current. If you fill a cup with river water and hold it still, you won't see the current. The water in the cup sits there, calm and motionless. But that same current, over the length of the entire river, is powerful enough to move boats, shape landscapes, carry millions of gallons of water to the sea. The current exists in the cup, technically speaking, but its effects only become noticeable across much larger distances. Dark energy is similar. It creates a gentle, constant, outward pressure everywhere in space. But this pressure is extraordinarily weak. On the scale of a room, a planet, even a galaxy, it's negligible. Gravity and other forces easily overpower it. The atoms in your body stay bound together. Earth orbits the Sun in a stable path. Our Milky Way galaxy holds together, its hundreds of billions of stars orbiting the galactic center. It's only when you look at the vast distances between galaxy clusters, across hundreds of millions or billions of light years, that dark energy's influence becomes dominant. At these scales, there's so much space for it to act across that its effects accumulate. The gentle push, repeated over and over across immense reaches of emptiness, adds up to something powerful enough to overcome the gravitational pull between distant galaxies. This is why the universe's acceleration wasn't obvious until we studied objects billions of light years away. Nearby galaxies, held together by local gravitational interactions, don't show the effect. But distant galaxies, separated by truly cosmic distances, feel dark energy's full force. They accelerate away from us and from each other, carried by the stretching of space itself. So dark energy surrounds you, fills you, exists in every place you've ever been. Yet it touches your life not at all, at least not directly, not in any way you could perceive. Its domain is the space between galaxy clusters, the vast cosmic voids, the largest structures in the universe. That's where dark energy rules, where its gentle pressure shapes the fate of everything. To truly feel how strange this is, to grasp what dark energy is actually doing to the fabric of space and time, we need to understand its properties more deeply. We need to see how it works, what distinguishes it from all other forms of energy, and why it creates this peculiar, accelerating push, rather than an attractive pull, like gravity does. At its most basic level, dark energy does one simple thing. It pushes. While gravity pulls everything together, dark energy pushes everything apart. These two forces, the pull and the push, have been competing throughout the entire history of the universe, and the balance between them has determined how the cosmos has evolved. Gravity is the force you're most familiar with. It keeps your feet on the ground, holds the moon in orbit around Earth, binds our solar system together, and pulls galaxies into clusters. every piece of matter in the universe pulls on every other piece through gravity. The more matter you have, the stronger the pull. Put enough matter in one place and you get a star, a planet, a black hole. Dark energy works completely differently. It doesn't depend on how much matter is present. It seems to be a property of space itself, meaning that the more space exists, the more dark energy there is. As the universe expands and creates more space, it automatically creates more dark energy. This might sound odd, like getting more water by pouring your glass into a bigger glass. But that's genuinely how it appears to work. This creates a fascinating dynamic. In the early universe, everything was packed closely together. Matter was dense, and its gravitational pull was enormously strong. Dark energy existed then too, but there was less space for it to fill, and matter's gravity dominated completely. The universe expanded, yes, but gravity was winning the tug of war, slowing down the expansion. As time passed and space stretched, matter spread out. The density dropped. Atoms that were once close neighbors found themselves separated by growing distances. And as matter thinned out, its collective gravitational pull weakened. Meanwhile, the expansion created more space, and more space meant more dark energy. The balance began to shift. For roughly the first 7 billion years of the universe's history, gravity was stronger. It slowed the expansion, though it couldn't stop it completely. The initial push from the Big Bang was too strong for that. But gravity did its job, acting as a brake, keeping the expansion rate in check. Then, around 7 billion years ago, something remarkable happened. The universe had expanded enough that matter had thinned out sufficiently for dark energy to take the lead. The push began to exceed the pull. And from that moment forward, the expansion started accelerating instead of decelerating. The universe began growing faster and faster. We live in the dark energy era now. Today, dark energy is the dominant force on cosmic scales. It's not that gravity has disappeared or stopped working. On local scales, within galaxies and galaxy clusters, gravity still rules. But in the vast spaces between these structures, dark energy reigns supreme. This transition from a gravity-dominated universe to a dark energy-dominated one marks one of the most significant changes in cosmic history. It altered the fate of everything. Before the transition, the universe's future was uncertain. Would expansion continue forever? Or would gravity eventually win and pull everything back together? After the transition, the answer became clear. Dark energy had won, and its victory was permanent. But this wasn't always true. Let's walk through the universe's history and watch how this cosmic balance shifted over time. We'll start at the very beginning, just after the Big Bang, when everything that exists was compressed into an impossibly small, impossibly hot state. In those first moments, matter and energy filled space with incredible density. Particles crashed into each other constantly. The temperature was trillions of degrees. Space expanded rapidly, driven by the explosive force of the Big Bang itself. Gravity pulled hard on all this matter, trying to slow things down. But the initial expansion was so violent that gravity couldn't stop it. As the universe cooled and expanded over the first few 100,000 years, matter began to clump together. Tiny variations in density, small regions where matter was slightly more concentrated, began to grow. Gravity pulled support more matter into these denser regions, creating the seeds of future galaxies. Dark energy existed during all of this, but it was completely overpowered by gravity's influence. The universe was too small, too dense, for dark energy to matter. Fast forward a few 100 million years. The first stars ignited, burning hydrogen into helium, lighting up the cosmos for the first time since the Big Bang's initial glow faded. Galaxies began to take shape, gathering billions of stars into rotating disks and elliptical clouds. Gravity was still firmly in control, pulling matter together, organizing it into larger and larger structures. For billions of years, this continued. Galaxies merged with other galaxies. Stars were born, lived, and died. The universe expanded, yes, but gravity slowed this expansion steadily. If you could have measured the expansion rate during this era, you would have seen it decreasing over time, getting slower and slower as gravity did its work. Think of it like a crowded party in a large room. When everyone first arrives, they're packed together near the entrance, talking closely, bumping into each other constantly. The social gravity, the pull of conversation and connection, keeps everyone clustered. But as people gradually spread out across the room, finding more personal space, those connections weaken. Distance grows between groups. The room starts to feel emptier. That's what happened to the universe. As galaxies spread apart and space grew between them, the gravitational bonds weakened. And as space expanded, dark energy's influence grew proportionally. More space meant more of this mysterious pressure pushing outward. Around 7 billion years after the Big Bang, the balance tipped. The universe had expanded enough. Matter had thinned out enough. That dark energy's push finally exceeded gravity's pull. The expansion rate, which had been steadily decreasing for billions of years, hit a minimum and then began to increase. The universe started accelerating. This wasn't a sudden flip, like throwing a switch. It was gradual, though. Smooth transition from deceleration to acceleration. But once it began, it continued. Dark energy's dominance grew stronger with each passing year as the universe expanded further, and matter thinned out more. We live roughly 7 billion years after that transition point. We're 14 billion years into a universe that started decelerating and is now accelerating. And this push is changing everything about our universe's future, reshaping the destiny of every galaxy, every star, every planet. Zoom out with me now to the largest scale we can imagine. Picture the universe as a vast tapestry of galaxies, billions upon billions of them, scattered through space like islands in an infinite ocean. Each galaxy contains hundreds of billions of stars. And right now, at this very moment, nearly all of them are racing away from us. The nearby galaxies, the ones in our local group, stay bound to us by gravity. The Andromeda Galaxy, our nearest large neighbor, is actually moving toward us. In a few billion years, it will collide with the Milky Way, and the two galaxies will merge into one. Gravity wins on this scale, holding our local neighborhood together despite dark energy's push. But look beyond our local group, beyond the few dozen galaxies held together by mutual gravitational attraction, and everything is fleeing. The Virgo cluster, a collection of thousands of galaxies about 50 million light-years away, recedes from us at over 1 million miles per hour. The Coma cluster, 300 million light-years distant, races away 3 times faster. Go farther still, and the speeds become staggering. Galaxies, billions of light-years away, are receding at a significant fraction of the speed of light. The most distant galaxies we can see, whose light has been traveling toward us for over 13 billion years, are moving away from us faster than any spacecraft humans could ever build. And here's something truly mind-bending. The most distant objects in the observable universe are receding faster than the speed of light itself. This might sound impossible. Einstein told us, nothing can move through space faster than light. But these galaxies aren't moving through space. Space itself is expanding, carrying them along. There's no speed limit on how far space can stretch. Imagine ants walking on a rubber sheet. The ants move at a steady pace across the rubber, never exceeding their maximum ant speed. But now, imagine the rubber itself is stretching. If it stretches slowly, the ants can make progress across it, moving from one edge toward the other. But if the rubber stretches fast enough, an ant could walk forward at full speed and still find itself farther from its destination than when it started, simply because the rubber beneath it is stretching faster than it can walk. That's what's happening with light from the most distant galaxies. The light travels toward us at light speed, the fastest anything can move. But space itself expands fast enough that the distance the light has to cross grows faster than the light can traverse it. Eventually, after billions of years, the light reaches us. But during its journey, the galaxy that emitted it has been carried to even more tremendous distances by the expansion of space. This acceleration means that galaxies which are already far away are getting farther away at an ever-increasing rate. The universe is not just growing, it's growing faster and faster with each passing moment. And this relentless acceleration creates something both beautiful and profoundly lonely. It creates boundaries, horizons, edges to what we can ever see or know or reach. There are galaxies out there, real physical places with billions of stars and countless worlds whose light will never reach us. Not because the light isn't traveling, not because something blocks its path, but because space is expanding too quickly between here and there. The light sets out on its journey toward us, racing through space at the cosmic speed limit. But space itself stretches faster than the light can cross it. The gap grows rather than shrinks. This creates what astronomers call the cosmic horizon, a boundary beyond which we cannot see. It's not a physical wall or edge. It's more like a horizon on Earth's surface. When you stand on a beach and look out at the ocean, you can only see so far before the curve of the Earth blocks your view. There's more ocean beyond that line, but you can't see it from where you stand. The cosmic horizon works similarly, except it's created by the expansion of space rather than Earth's curvature. There's more universe beyond this boundary. Galaxies exist there, stars shine there, perhaps planets orbit, and life evolves there. But we will never see any of it. Their light will never reach us. They exist in a part of the universe forever separate from our own. And this horizon is not fixed. It's actually shrinking. As the universe's expansion accelerates, more and more galaxies cross this boundary, slipping beyond our ability to ever observe them. Galaxies we can see today will eventually disappear from view, not because they stop shining, but because space will stretch so much between us and them that their light can no longer reach us. Imagine standing on a shore watching ships sail away. At first, you see them clearly, every detail visible. As they move farther out, they become smaller, harder to see. Eventually, they disappear over the horizon. But if that horizon were somehow moving closer to you, shrinking the visible ocean, you'd watch more and more ships vanish, even ones that hadn't traveled very far yet. That's happening to our universe. The cosmic horizon is contracting. In the far future, trillions of years from now, intelligent beings living in our galaxy would look out and see almost nothing. The nearby galaxies in our local group would still be visible, held close by gravity, but everything else would have vanished beyond the horizon. The universe would appear to consist of just one small island of galaxies surrounded by eternal darkness. They would have no way to know the universe had ever been larger, more populated, more connected. The evidence would have literally sailed beyond the edge of what's observable. If they developed astronomy and cosmology, they might conclude they lived in a small, static universe containing just their local group and nothing more. We're fortunate. We live at a time when the universe is still relatively young, when most of it remains visible to us. We can look out and see billions of galaxies, trace the history of cosmic expansion, discover dark energy through its effects on distant supernovae. But here on Earth, in this moment, we can still see billions of galaxies, and each one tells us more about this mysterious force that's reshaping the cosmos. Let's take a moment to gather what scientists have actually learned about dark energy through decades of careful observation and measurement. These are the facts, the things we can say with confidence, even though they raise as many questions as they answer. First, dark energy makes up about 68% of all the energy in the universe. This is a remarkably precise measurement, confirmed by multiple independent observations. When you add up everything that exists, all the matter and energy in the cosmos, dark energy accounts for more than 2/3 of it. Regular matter, the atoms that make up stars and planets and people, represents less than 5%. The remaining 27% is dark matter, another invisible component we detect through its gravitational effects. Second, dark energy appears to be spread evenly throughout space. Unlike matter, which clumps together to form stars and galaxies, dark energy maintains a constant density everywhere. There's the same amount of dark energy in the vast voids between galaxy clusters as there is within galaxies themselves. It doesn't gather, it doesn't concentrate, it simply fills all of space uniformly. Third, dark energy seems to stay at the same strength over time. As the universe expands and creates more space, the density of dark energy remains constant. This is strange. When you have a certain amount of matter and you spread it through a larger volume, its density decreases. But dark energy doesn't work that way. More space means more dark energy, as if space itself generates it. Fourth, dark energy creates negative pressure. In physics, pressure is usually something that pushes outward in all directions, like air inside a balloon pushing against the rubber. But dark energy creates a kind of tension or suction that paradoxically causes space to expand faster. This negative pressure is what drives the acceleration. It's what makes dark energy push rather than pull. Fifth, dark energy appears to have been present throughout the universe's entire history, though its effects only became dominant relatively recently in cosmic terms. When scientists look at distant supernova and map out the expansion history, they can see the transition from deceleration to acceleration happening around 7 billion years ago. Before that, dark energy existed, but was too weak to overcome gravity. After that point, it took over. These facts form a strange portrait. Dark energy is everywhere, always at the same strength, creating a pressure that makes space expand faster. It's the dominant component of reality, and yet it remains almost completely mysterious. We can measure what it does with impressive precision. We can calculate its density. We can track how it's affected the universe's growth over billions of years. But knowing what something does isn't the same as understanding what it is. Scientists have proposed various explanations for what dark energy might be, each with its own implications and challenges. The leading idea connects it to something called the cosmological constant, a concept that dates back to Einstein. But even this explanation comes with profound mysteries attached. Knowing what it does isn't the same as knowing what it is. The leading explanation for dark energy is both elegant and deeply puzzling. Scientists think it might be a property of empty space itself, a kind of energy that exists in the vacuum. The idea is that space, even when completely empty of matter and radiation, isn't truly nothing. It has energy built into its very structure. This concept has roots in quantum mechanics, the physics of the very small. According to quantum theory, empty space isn't calm and still. It's actually buzzing with activity. Virtual particles constantly pop into existence in pairs, exist for the briefest instant, then annihilate each other and disappear. These quantum fluctuations happen everywhere, all the time, even in the deepest vacuum. Think of empty space like the surface of a calm pond. From far away, it looks perfectly still, perfectly smooth. But look closer, and you see tiny ripples, microscopic movements, vibrations at the smallest scales. The water is never truly motionless. Empty space is similar. At quantum scales, it seethes with energy. This quantum energy of the vacuum could, in principle, create the kind of negative pressure we associate with dark energy. It would be a fundamental property of space itself, present everywhere, constant in strength, unchanging over time. This explanation, called the cosmological constant, because it represents a constant energy density in space, matches our observations remarkably well. There's a beautiful simplicity to this idea. The more space exists, the more vacuum energy there is. As the universe expands, it creates more space, which means more dark energy, which drives faster expansion, which creates even more space. It's a self-reinforcing cycle that naturally leads to accelerating expansion. Einstein actually introduced something like this idea over a century ago, though for different reasons. When he first applied his theory of general relativity to the universe as a whole, he found that the equations predicted a universe that either expanded or contracted. They couldn't describe a static, unchanging cosmos. But in Einstein's time, everyone believed the universe was static and eternal. So, Einstein added a term to his equations, a cosmological constant that could balance gravity and keep the universe still. It was a mathematical adjustment, a way to make the theory fit what people believed about reality. Then Hubble discovered that the universe was expanding after all, and Einstein called adding the cosmological constant his biggest mistake. He removed it from his equations. But now, a century later, scientists have brought it back. The accelerating expansion, discovered in 1998, suggests that something very much like Einstein's cosmological constant exists after all. The universe needs that extra term in the equations. Empty space does have energy. Einstein's mistake might have been removing it. Yet this explanation, despite its elegance, comes with a staggering problem. When physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer, and that answer is wrong. Spectacularly, enormously, incredibly wrong. It's off by a factor so large that it represents one of the biggest mismatches between theory and observation in all of science. This creates its own mystery, one that deepens the puzzle rather than solving it. When physicists calculate how much energy the vacuum should have, according to quantum mechanics, they get a number. When they measure how much dark energy actually exists by observing the universe's expansion, they get a different number. These two numbers should match. They don't, not even close. The predicted value is larger than the observed value by a factor of about 10 to the power of 120. That's a 1 followed by 120 zeros. To put this in perspective, there are only about 10 to the power of 80 atoms in the entire observable universe. The mismatch between theory and observation is so vast that it dwarfs every other scale we can imagine. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. If quantum mechanics is right about vacuum energy, the universe should be expanding so fast that galaxies, stars, even atoms couldn't exist. Space would tear itself apart almost instantly. But that's not what we see. Instead, we observe a very gentle, slow acceleration that only becomes noticeable across billions of light years. Something must be cancelling out nearly all of the vacuum energy that quantum mechanics predicts. Some mechanism, some principle we don't understand, must be reducing that enormous predicted value down to the tiny observed value. But nobody knows what that mechanism is, or why it would work so precisely. It's as if you tried to balance your checkbook and found that your predicted balance was $1 trillion, but your actual balance was $10. Something is clearly wrong with either your calculation or your understanding of how money works. In physics, we face a similar situation. Either our calculations are missing something fundamental, or our understanding of how vacuum energy works is incomplete. Scientists have proposed various solutions. Maybe there's some symmetry in nature that forces most of the vacuum energy to cancel out, leaving only a tiny remainder. Maybe quantum gravity, the still undiscovered theory that unites quantum mechanics and general relativity, will explain why the vacuum energy is so small. Maybe we're thinking about the problem in the wrong way entirely. But so far, no solution has proven satisfactory. The cosmological constant problem remains unsolved, a giant question mark sitting at the foundation of our understanding of the universe. We observe dark energy causing acceleration. We think it might be vacuum energy, but we can't explain why it has the value it does. This kind of mystery, frustrating as it is, represents the frontier of science. It's where our current theories break down, where new discoveries wait. Every major breakthrough in physics has come from confronting problems like this, contradictions between what we expect and what we observe. And there's another possibility, one that makes the puzzle even more interesting. Maybe dark energy isn't the cosmological constant at all. Maybe it's not a property of empty space, but something else entirely, something we haven't thought of yet. Scientists have explored several alternative ideas, each offering a different perspective on what dark energy might be. Perhaps dark energy isn't constant at all. Maybe it changes over time, growing stronger or weaker as the universe ages. Scientists call this possibility quintessence, named after the ancient Greek idea of a fifth element that filled the heavens. Unlike the cosmological constant, which stays perfectly steady, quintessence would be a dynamic field that evolves. Imagine a ball rolling down a hill. At the top, it moves slowly. As it descends, it picks up speed. The ball's energy changes as it rolls. Quintessence would be similar, a field that changes strength over cosmic time. Maybe it was weaker in the early universe and has grown stronger. Or maybe it started strong and is slowly fading. Current observations can't quite tell the difference between constant dark energy and slowly changing quintessence, but future measurements might. Another idea suggests dark energy isn't a thing at all, but rather a sign that gravity works differently on cosmic scales than we think. Einstein's general relativity has passed every test we've thrown at it, accurately describing how gravity works near Earth, around the Sun, even near black holes. But maybe at the scale of galaxy clusters and beyond, gravity behaves in ways Einstein's equations don't capture. If this is true, what we're calling dark energy might just be our misunderstanding of gravity itself. The accelerating expansion wouldn't be caused by mysterious energy filling space, but by gravity being weaker or working differently across vast distances. Scientists have proposed various modified gravity theories, though so far none matches observations as well as the simpler explanation of dark energy existing. There's another intriguing possibility. Maybe dark energy is an interaction between our universe and something beyond it. Some theories in physics suggest our universe might be one of many, floating in a higher dimensional space. If that's true, perhaps what we perceive as dark energy is actually the influence of other universes, their gravity or energy affecting ours across dimensions we can't directly observe. This sounds like science fiction, but it's based on serious mathematics. String theory and other attempts to unify physics suggest extra dimensions beyond the three of space and one of time we experience. If these extra dimensions exist, they could harbor other universes, other realities, perhaps even other forms of matter and energy. The accelerating expansion might be our universe's response to these hidden influences. Scientists have even considered whether dark energy might be connected to the way information works at cosmic scales, or whether it emerges from the quantum entanglement of particles across vast distances. These ideas push the boundaries of current physics, exploring possibilities that seem almost magical, but are grounded in mathematical frameworks. What all these alternatives have in common is that they're attempts to explain the observations without requiring a cosmological constant with its troubling calculation problem. They're different ways of thinking about why the universe accelerates, each with its own predictions and challenges. Testing these ideas requires extremely precise measurements of how dark energy has affected the universe over time. Scientists need to map out the expansion history in great detail, looking for any hint that dark energy has changed strength or behaves differently than a simple constant. Whatever dark energy is, it's shaping the most fundamental question of all about our existence. Dark energy isn't just an interesting cosmic curiosity. It determines the ultimate fate of everything that exists. The future of every galaxy, every star, every planet, every possible form of life depends on what dark energy does over the coming trillions of years. If dark energy remains constant, as most evidence suggests, the universe will expand forever at an accelerating rate. Galaxies beyond our local group will continue moving away faster and faster. Over billions of years, they'll disappear beyond the cosmic horizon one by one, their light unable to reach us anymore. The universe will grow darker, emptier, more isolated. In about 4 billion years, our Milky Way will collide with Andromeda, and the two galaxies will merge into one larger galaxy. Other nearby galaxies might join this merger, creating a single massive island of stars. But everything beyond our local group will have vanished from view, accelerated away beyond the boundary of what we can observe. The stars will continue burning for a while, fusing hydrogen into helium, helium into heavier elements. New stars will form from the remaining gas, but eventually, over trillions of years, the raw materials for star formation will be used up. The last stars will flicker and die, leaving behind only cold remnants. White dwarfs, neutron stars, black holes. The universe will grow profoundly dark. No more starlight, no more galaxies visible in any direction except our own merged cluster. Just darkness, cold, and the inexorable expansion of space continuing forever. This scenario is sometimes called the Big Freeze or heat death, a universe that slowly runs down like a clock nobody winds. But it's not violent, it's not catastrophic. It's gentle, peaceful, a long, slow fade, rather than a sudden end. Stars will have lifetimes measured in trillions of years, Even after they die, their remnants will persist for unimaginable spans of time. Black holes will eventually evaporate through a quantum process called Hawking radiation, but that takes so long that the numbers become almost meaningless. We're talking about 10 to the power of 100 years or more for the largest black holes to evaporate. That's a Google years, a number so vast that the current age of the universe, 14 billion years, is essentially zero in comparison. The universe will exist in this dark, empty, expanding state for timescales that dwarf all of cosmic history so far. Yet even in this far future, there's a kind of serenity to it. The universe won't end in fire or collapse. It will simply continue, growing larger and cooler and emptier, but never truly ending. Space will keep stretching. Time will keep flowing. The laws of physics will keep operating, even if there's almost nothing left for them to act upon. This is the fate dark energy has written for the cosmos, assuming it stays constant. A universe that expands forever, gradually losing complexity, structure, and light, but persisting eternally in an ever thinner, ever colder state. It's a quiet conclusion to a story that began with the violent brilliance of the Big Bang. But that's trillions of years away. Right now, something else is happening. Something that makes our moment in time remarkable. Right now, even as dark energy pushes galaxies apart and accelerates the universe's expansion, new stars are being born. In the Orion Nebula, just 1,500 light-years away, gas clouds are collapsing under gravity, heating up, igniting fusion. Baby stars are opening their eyes for the first time, beginning lifetimes that will last millions or billions of years. Planets are forming too. Around young stars throughout the galaxy, disks of dust and gas are clumping together, building worlds grain by grain. Rocky planets like Earth, gas giants like Jupiter, ice worlds in the outer reaches of solar systems. Each one is a new place, a new collection of atoms arranged in unique ways, with its own story waiting to unfold. Life might be starting somewhere right now. On a warm planet orbiting a stable star, simple molecules might be assembling into more complex forms. The first self-replicating chemicals could be emerging, taking those initial steps toward biology, toward evolution, toward consciousness. Or perhaps life is already well established on countless worlds, thriving in oceans and atmospheres and environments we can barely imagine. The universe is both expanding and creating, both growing apart and coming together. Dark energy dominates the largest scales, pushing galaxy clusters away from each other. But within galaxies, gravity still wins. Stars orbit galactic centers, planets orbit stars, moons orbit planets. The dance of attraction continues, building structure even as the cosmic backdrop stretches. This is the beautiful tension at the heart of our universe. Two opposing forces, expansion and attraction, both operating simultaneously at different scales. Dark energy determines the ultimate fate of the cosmos. Yes. It ensures that eventually, after trillions of years, star formation will cease and the lights will go out. But that's not today. That's not for an incomprehensibly long time. Today, the universe is alive with activity. galaxies collide and merge, triggering bursts of new star formation. Supernovae explode, scattering heavy elements into space, seeding future generations of stars and planets with the raw materials for complexity. Black holes at galactic centers devour matter and spray out jets of energy. Pulsars spin, quasars shine, nebulae glow with the light of newborn stars. As you rest here tonight, somewhere in the universe, a star is being born. Somewhere, a planet is forming. Somewhere, perhaps, the first living cell is dividing, beginning a chain of evolution that might eventually lead to intelligence, to awareness, to other beings looking up at their own night sky and wondering about their place in the cosmos. Dark energy may be shaping the future, but it doesn't control the present. Right now, in this era of cosmic history, the universe is still rich and dynamic and full of possibilities. We exist in a time when stars still shine brightly, when galaxies fill the sky, when creation and destruction balance each other in an ongoing cycle of renewal. This won't last forever in cosmic terms, but it will last for billions of years more. Plenty of time for countless stories to unfold, for new worlds to form, for life to emerge and evolve, and perhaps reach out to touch other life across the vast distances between stars. And this brings us to a deeper question about our particular moment in time. We live in a special time, not special in the sense that the universe was created for us, or that we're at the center of anything. Special simply because of when we exist in the cosmic timeline. We've arrived at a moment when the universe is still young enough to be interesting, still old enough to have developed complexity, and still transparent enough to be understood. 14 billion years have passed since the Big Bang. That's long enough for heavy elements to form in stars and spread through space. Long enough for planets to coalesce and life to emerge. Long enough for evolution to produce beings capable of looking up and asking questions about their origins. We exist because the universe has had time to create us. But we also exist early enough that the universe is still full of light. When we look up at the night sky, we see thousands of stars with our naked eyes, billions with telescopes. We can observe distant galaxies, study their properties, measure their distances and motions. The evidence of the Big Bang, the cosmic microwave background radiation, is still visible, still carrying information about the universe's earliest moments. If we had been born trillions of years in the future, none of this would be true. The sky would be nearly empty. The cosmic microwave background would have been stretched and redshifted into invisibility. Most galaxies would have disappeared beyond the cosmic horizon. Any astronomers in that distant era would have almost no evidence of the wider universe, almost no way to discover cosmology or the Big Bang or dark energy. They would look out from their galaxy and see nothing but darkness. They might conclude they lived in a small, isolated universe. They would be wrong, but they'd have no way to know it. The information would have literally expanded away from them, carried beyond the boundary of the observable. We're fortunate to exist in what you might call the universe's bright era, when stars still shine, when galaxies still cluster together in visible patterns, when the history of cosmic expansion is written in the light from distant supernova. We can study the universe because we live in a time when the universe is still studyable. There's something almost poetic about this. We exist in a narrow window of cosmic time, after complexity has emerged, but before isolation sets in. We're here when the universe is old enough to have created observers, and young enough that those observers can still see what they're part of. It's as if the universe has arranged for witnesses to its own story right at the moment when the story is most complete and most visible. This isn't evidence of design or purpose. It's just timing, just chance, just the natural unfolding of physical law. But it's still remarkable. We could have existed at any point in cosmic history, and we happen to exist at one of the few periods when understanding the cosmos is actually possible. Dark energy will continue reshaping the universe over the coming eons. It will spread galaxies apart, darken the sky, erase the evidence of cosmic history. But right here, right now, in this brief window of cosmic time, we can see it all. We can trace the expansion, discover the acceleration, infer the existence of this invisible force that fills everything. And there's something remarkable about how we even discovered this invisible force in the first place. Think about what it took to discover dark energy. Scientists had to study exploding stars billions of light years away, so distant that their light had been traveling through space since before Earth formed. They had to measure the brightness of these explosions with incredible precision, comparing what they saw with what they expected. They had to analyze the spectrum of light, looking for tiny shifts toward the red that revealed how fast these distant galaxies were receding. These measurements required some of the most sophisticated telescopes ever built, instruments that could gather the faint light from objects at the edge of the observable universe. It required digital cameras sensitive enough to detect individual photons. It required computers to process vast amounts of data, comparing hundreds of supernovae, looking for patterns in the measurements. But beyond the technology, it required imagination. When the first results came in showing that the universe's expansion was accelerating, the scientists' initial reaction was disbelief. They checked their data again and again, looking for mistakes. The result was so unexpected, so contrary to what everyone thought they knew, that accepting it meant being willing to overthrow decades of assumptions about how the universe worked. Two teams worked on this independently, each checking the other's results. When both arrived at the same conclusion, the scientific community had to take it seriously. The universe was accelerating. Something invisible was pushing it apart. The evidence was too strong to ignore. This is how science advances, not through sudden flashes of insight, though those help, but through careful measurement, patient analysis, and the humility to accept when nature surprises you. The discovery of dark energy came from looking at tiny points of light in telescopes and being willing to follow the data wherever it led, even into mystery. Nobody set out to discover dark energy. The scientists were trying to measure how much the expansion was slowing down, expecting to find a number that would tell them whether the universe would expand forever or eventually collapse. Instead, they found it was speeding up. They stumbled onto one of the biggest discoveries in the history of cosmology while looking for something else entirely. And they could only do this because of all the knowledge built up over centuries by thousands of other scientists. Understanding light and how it shifts with motion. Understanding stars and how they explode. Understanding distance measurement in astronomy. Understanding general relativity and how gravity affects space and time. Each piece of this puzzle was contributed by different people working on different problems, building a foundation that eventually let others discover something none of them anticipated. It's a triumph of human curiosity, this ability to detect something that doesn't emit light, doesn't absorb light, doesn't clump or cluster, or do anything directly observable. We found it by looking at what it does, by studying its effects on things we can see. We mapped out an invisible force by watching how it moves visible objects across billions of light years. And the search continues. New telescopes are being built. New surveys are mapping more of the sky. New experiments are probing the nature of space and time at the quantum level. Scientists are gathering more data, making more precise measurements, looking for any hint of what dark energy truly is. New telescopes are coming online, instruments more powerful than anything that came before. The James Webb Space Telescope, launched recently, can peer deeper into space and further back in time than Hubble ever could. Ground-based observatories with enormous mirrors are being built, designed to gather light from the faintest, most distant objects. These new tools will map the universe in unprecedented detail. They'll study thousands more supernovae, tracking how the expansion rate has changed across cosmic history. They'll measure the clustering of galaxies, looking for the subtle imprint dark energy leaves on the cosmic web of matter. They'll observe how dark energy affects the growth of structure in the universe over billions of years. Scientists are also looking for any sign that dark energy has changed over time. Even a tiny variation in its strength, a small deviation from being perfectly constant, would be enormously significant. It would rule out the cosmological constant and point towards something more dynamic, like quintessence. The measurements need to be incredibly precise to detect such subtle changes. But that's exactly what these new surveys are designed to do. There are other approaches too. Physicists are studying the cosmic microwave background, the afterglow of the Big Bang, looking for patterns that might reveal something about dark energy's nature. They're measuring how light from distant galaxies bends around massive clusters, mapping the distribution of matter and dark energy through gravitational lensing. Some experiments are even trying to detect dark energy directly in laboratories here on Earth. If dark energy is connected to quantum vacuum fluctuations, perhaps incredibly sensitive instruments could measure its effects on tiny scales. These experiments push the boundaries of measurement technology, looking for the faintest whispers of a force that operates most strongly across cosmic distances. Each new piece of data adds to the puzzle. Scientists are building a detailed map of how dark energy has shaped the universe's growth, how it competes with gravity, how it determines the fate of cosmic structure. They're narrowing down what it could be, ruling out theories that don't match, observations, refining their understanding year by year. The hope is that eventually enough clues will accumulate that the mystery starts to crack. Maybe a pattern will emerge in the data that points toward a specific theory. Maybe a breakthrough in quantum gravity will suddenly make sense of the cosmological constant problem. Maybe an entirely new idea, something nobody has thought of yet, will emerge from the observations. Or perhaps dark energy will remain mysterious for decades or centuries more. A question left for future generations to solve. Science doesn't always move quickly. Some problems take time, require new technologies, new mathematical frameworks, new ways of thinking that aren't yet available. But that's okay. The mystery is part of the beauty. Not knowing everything makes the universe more interesting, not less. Each question we answer reveals new questions we didn't know to ask. Each discovery opens doors to deeper mysteries. Right now, we're in the midst of a golden age of cosmology, gathering data about the universe at an unprecedented rate. We may be closer to understanding dark energy than we think, or we may be just at the beginning of a long journey. Either way, the search continues, patient and persistent. But even as we learn more, one truth remains constant. We've traveled far together tonight, from the invisible force that fills everything to the distant galaxies racing away at impossible speeds. From the moment of discovery in 1998 to the far future when the stars will dim and the universe will grow dark and cold. From the quantum buzz of empty space to the vast cosmic scales where dark energy shapes everything. And through it all, one truth has remained. The universe is larger and stranger than we imagined. Most of what exists is invisible to us. The dominant force in the cosmos is something we're only beginning to understand. Mystery surrounds us, fills us, permeates every moment of our existence. But that's not something to fear. Mystery is beautiful. Not knowing everything means there's always more to discover, more to wonder about, more to explore. The universe keeps its secrets, yes, but it also offers clues, leaving traces in the light from distant stars, writing its history in the patterns of galaxies scattered across space. Right now, as you rest here in this quiet moment, dark energy is all around you. It fills the space between your hands, the air in your lungs, the room you're in. It's pushing distant galaxies apart, stretching space itself, reshaping the cosmos on scales almost too vast to comprehend. And yet, here you are, held together by forces stronger than dark energy. Your atoms bound by electromagnetism, your body held to earth by gravity, your thoughts flowing through patterns of connection in your brain. You exist in a universe that's both expanding and creating, both mysterious and knowable, both ancient and still young. The same laws that govern the motion of galaxies govern the beating of your heart. The same atoms that formed in the cores of dying stars make up your body. You're connected to all of this, part of the cosmic story, made of stardust and shaped by the same forces that shape everything. We've journeyed from wonder to wonder tonight, exploring one of the deepest mysteries in all of science. If you've enjoyed this exploration through the cosmos, if these quiet moments of scientific discovery bring you calm or spark your curiosity, I'd love for you to like this video and subscribe to the channel. It helps other wanderers find their way here, helps us build a community of people who love learning about the universe as they drift towards sleep. And let me know in the comments what aspect of dark energy fascinated you most, or what cosmic mystery you'd like to explore next time. Rest well in this vast, mysterious, expanding cosmos. Good night.